And what we're looking at today is we're really going to get deep into some numbers today. And so we ended our talk on Friday by discussing the concept of significant figures. Significant figures are what we use to help us describe just how good, how accurate, how precise a measurement actually is. The more significant figures that we have, the more precision, the more accuracy, the better confidence that we can have in a particular number for a measurement. For example, if we take a measurement of mass and we do it on, a bathroom scale, we will get a measurement. It may not necessarily be all that precise. And so there's a little bit of uncertainty that would be associated with that measurement. Whereas if we took the same object, measured it on a balance that gave us 4 decimal places, we would say that we have a much better idea of how much that particular substance weighed on that 4 decimal place balance compared to our bathroom scale. So when we measure values ourselves, there's always uncertainty involved in that. If we are given measurements, these rules for significant figures play an important concept in determining how precise, how good a measurement is. So what we need to look at then are using these rules to help us to figure out how good a measurement could be or is. And so what we'll end up doing is let's go through some of these here together. And based upon the rules for significant figures that we identified in Friday's lecture, let's put a number to how many significant digits are present here in these figures. So if I'm given the number 26, how many significant digits are in that number 26?
Two.
Yes, it's just 2. Remember, our rules for significant figures always are going to include non-zero digits. So if I have digits that are non-zero, I have to assume that they are significant based upon our rules. Now, what about this next one? 19,628.00.
5.
Okay, I've got a 5. Anyone else? Okay. All right, I'm seeing some 7s in the chat, and 7 would be correct. Why 7? Well, we know that these 5 non-zero numbers are definitely significant. The question is what to do with those zeros at the end. And remember, for a 0 to count, it has to have 2 things going for it. First of all, it has to be after a non-zero number. So we've got that. These zeros are after non-zero numbers here. So first criteria is met. Second criteria is we've got to have a decimal point. Decimal point right there satisfies the second condition. That means that those zeros are both significant, which means that we have 7 total significant digits in this number. All right, what about our third number? 0.003416. right, I'm seeing a little bit more variability this time around. Okay, now we're getting a little more consistent. So the answers seem to be falling into, it's either 6 or it's 4. It's either 6 or it's 4. Now, which one is it? Again, it comes down to, we know that there are 4 non-zero digits. So we know that there are at least 4 significant figures here. What do we do with these zeros? So again, it has to come down to what is significant and what is not significant. And so the 2 criteria, the zeros have to follow a non-zero number. These zeros do not follow a non-zero number. So even though there's a decimal point in there, these are not significant digits. 4 is the correct answer. All right, the last 2 here, I want you to try here on your own here. So 9 times 10 to the negative, or 10 to the 19th, 1.2407661 times 10 to the negative second. Go ahead, take a couple of seconds, write down your answers, and we'll talk about them together. All right, so let's come to these. For this one, 9 times 10 to the 19th. Remember, anytime we have scientific notation like this, scientific notation is 2 parts. There is the number and there is the exponent. The number will always have exactly the correct number of significant figures in it. So since 9 here is all that we have, there's only 1 significant digit. The rest of those zeros that follow that 9 are not significant figures. They're all just placeholders to allow us to get to a number of that large magnitude. In this last one, same deal. We've got a number and we've got an exponent. The number has the exact amount of significant figures in it that we're supposed to. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 digits, 8 significant figures. Any questions about how to determine the number of significant figures from a given measurement using our rules. All right, so then let's move on a little bit. Talking about scientific notation now. In scientific notation, as I've mentioned before, scientific notation, it consists of two parts. There is the number, or more commonly referred to as the coefficient, and then there is the exponent. Those are the two parts, the number or coefficient and the exponent. The coefficient tells you the correct number of significant figures that are supposed to be in the measurement. The exponent tells us how many places I need to move that decimal left or right to get to the correct value of the number. And so these directions are specifically for how to get a number to scientific notation. So if I'm trying to get a number that is in decimal form into scientific notation, this is what I need to do. I determine the value of C by taking that decimal point, putting it between the first two significant digits, and then I determine the value of the exponent based upon how many places I have to move that to the left or the right to get to the number that I have. If I need to move the decimal place to the left, so if I start with a large number, like 305,000, to put it into scientific notation, I am going to first make a decimal 3.05, and then the trick is, if this is where my decimal point is going to be, to get the value of the exponent, how many places do I have to move that decimal point? So if it starts here, I went 1, 2, 3, 4, 5 places to the left. If I move it to the left, n is positive. This is 3.05 times 10 to the 5th. If I had a really small number, like 0.00019, my first step would be to relocate that decimal point. It's going to go right here now. So I have 1.9. How many decimal places did I move over? Well, from the starting position, it was 1, 2, 3, 4. This is 1.9 times 10 to the negative 4th. So the number of decimal places that I move has everything to do with the exponent. If I'm moving over to the left, then I'm going to have a positive exponent. If I'm going to move it over to the right, I have a negative exponent. Another way of thinking about this, Positive exponents are for large numbers. Negative exponents are for small numbers. So you should be able to kind of figure your way through and determine which one is supposed to be there, which one you're supposed to have. So just as a point of reference here, we can see that this column here on the left refers to numbers that we would record in decimal form. In every case, if I have a large number, that decimal point is there at the end. To turn it into scientific notation, I need to express the significant figures. So in each of these first three cases, the coefficient is 3.245. And the exponent is based upon how I moved the number, how I moved the decimal place. So I went 1, 2, 3 places over. That's where that exponent of 3 comes from. In this one, I moved 1, 2, 3, 4, 5, 6 places to the right. And so moving it to the right gives me the negative. 6 places gives me the 6. And in the last one, 1, 2, 3, 4, 5, 6, 7, 8, 9. I moved 9 places to the left. My exponent was positive 9 as a result. So we can see every single case of scientific notation follows this kind of pattern, where I'm moving things from one side to the other as necessary to meet some kind of goal in particular. And notice also that my coefficients always convey the appropriate number of significant figures for the value. So this number had 5 significant figures. We see a coefficient here that had 5 significant figures. This number has 2 significant figures. Its coefficient has 2 significant figures. This decimal had 3 sig figs, and 3 sig figs show up in the coefficient there. So anytime we have scientific notation, significant figures are going to be naturally rolled into that as part of the discussion. Automatically going to be there. There's never going to be any ambiguity with significant figures. All right, so the first one. So in this first one, we had 3,245. And so to move the point from the end, so the decimal point was here at the end of the number. To move it to the appropriate place between the first 2 significant figures, that means I had to move it here. To go from here to here required me to move the decimal place 3 times. Once, twice, 3 times. Since I moved it to the left, that means that it's going to be a positive exponent. And so I moved it to the left 3 places. This is a positive 3 exponent as a result. Any other questions regarding kind of our basic ideas, our basic construction of scientific notation? All right, so let's move on to something else then. Now, when it comes to scientific notation, There's another direction that we can go with it, and that is using your calculator. Being able to do calculations using your calculator and its scientific notation function is a really important skill. And the reason why it's important is because it's going to save you a lot of time, first and foremost. And second, it's going to limit errors, because a lot of times when we're doing scientific notation with multiplication or division, our order of operations always needs to be something we consider. Your calculator always does things by order of operations. And so if you tell it to do something like multiply by 10 to the 17th, it's going to do so. But if that was in the denominator of a fraction, it might actually come out with the wrong answer. So I'm going to switch cameras here real quick and show you how to do scientific notation on your so what we have here, this is a Casio model scientific calculator. And if you have one of these, your scientific notation button is this exponential button right here. So what you would want to do is, let's say I want to put in the number, and we'll just do a test number for both of these. The test number is going to be 3.5 times 10 to the 12th. So with any of these models, the way that you do it is you put in the coefficient first. 3.5 is my coefficient. Now, to turn it into scientific notation on a Casio, I'm going to hit the exponent button, and it's going to give me that. And then I'm just going to put in the value, 12. 3.5 times 10 to the 12th, that is how it's going to show up in my Casio here. If I hit enter, that's what it would show up. On a TI, this is the TI-30X. This is probably pretty similar to most of your scientific calculators. If you have something that is slightly different, what you might find is that this EE function is buried under your secondary functions. Sometimes it's buried under like secondary comma or something along those lines. The idea is pretty much the same though. 3.5 E 12. Same idea, same construction. Now, other different models of TIs might actually put in the times 10 to the part of it, and that's fine. The idea is the same in either way. So if you need to put in a negative exponent, the button that you're going to hit is your plus minus button. That switches it from negative to positive. So if I wanted it to be 3.5 times 10 to the negative 12th, this is the button that I hit there. Same is true for the Casio. 3.5 times 10 to the 12th. If I want negative 12, I just hit my push plus minus button. It turns it into negative 12. In scientific notation mode, you can do calculations with scientific notation just like this. If I want to multiply by 3.5, it'll do what I need it to do. Give me the exact same answer. And again, the value here is the scientific notation. This is 1.225 times 10 to the negative 11th. So this is something that you're going to have to play with individually. You're going to have to look at, because every calculator is a little bit different. But If you can master this particular skill, it does help significantly in improving your accuracy and improving your speed at which you calculate and solve problems. So let's do some practice. Let's convert the values here as shown in decimal form into scientific notation. Now this first one, we can see here that we've got 9,655.00. Now, unfortunately for us, since scientific notation has to include all of those significant figures, all of these values are significant according to our significant figures rules. So they're all going to show up in the scientific notation. For the coefficient, remember, since all these values are significant, we move the decimal point from here to between the first two significant digits, which would be right here. So our coefficient, 9.00000065500. All of those values are significant according to our significant figures rules. What's our exponent? Well, we need to move the decimal from here to here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So our exponent here is 10 to the 9th. It is a positive 9 because we moved the decimal place that direction. We moved it to the left. So our exponent there is positive. For the second one, we want to move the decimal place from here to here. The first two non-zero digits, the first two significant figures are the 8 and the 3. So our coefficient is 8.34 times 10 . We're going to move the decimal place 1, 2, 3, 4, 5, 6 places to the right. We're moving to the right. So that's a negative exponent. We just said 1, 2, 3, 4, 5, 6. So this would be the negative 6th power. Okay, for number 3 here, 1.21. Well, this is kind of a tricky one. In this, we know that the decimal point is supposed to go between the first two significant digits. In this case, it's already there. So we didn't move the decimal place left or right. We didn't move it at all. Our coefficient is 1.21. Our exponent here is actually 0 because we didn't move the decimal place at all. So yeah, you got that right, David. Okay, this next one, 14.82. We are going to move the decimal place one spot to the left, our coefficient is 1.482 times 10. We moved it one place to the left. We moved it to the left. So that's a positive exponent. It's 10 to the first. For this one, 299,800,000. We have to recognize there is no decimal place here. So only these numbers are significant. So my coefficient is 2.998. I'm starting here, I'm ending here. 1, 2, 3, 4, 5, 6, 7, 8. I went to the left, so it's a positive 8. 2.998 times 10 to the positive 8th. Last one here, 63. My coefficient is going to be 6.3. I'm moving the decimal place from here to here. So I went to the left, that's a positive number. I went one place, so it's 10 to the first. All right, any questions about scientific notation and how to get a number into scientific notation? So it looks like, for the most part, we seem to be there. So let's move on. When it comes to scientific notation, again, 3 primary functions that you can do in your calculator. You can multiply with scientific notation, you can divide with scientific notation, and you can raise numbers to a power within scientific notation. Each of these are done relatively simply, as I showed you on the calculator before, how to put in scientific notation. All you need to do with any of these is just simply use them as any other number in your calculation. So if you need to multiply it, you put in the number in scientific notation, you hit that multiply button, and then you put in whatever you're multiplying it by. Same thing with division. Same thing with raising it to a power. Now, the only thing that is different, and this varies by calculator model, is what does that input look like? How do you have to ultimately do it? And so if you have specific questions about your calculator, reach out to me. We can talk about your specific model at another time. For now, let's go ahead and do some practice here. So we have 6.78 times 10 to the third multiplied by 5.55 times 10 to the negative fourth. I'm going to flip my camera over to my calculator here. And of course it's backwards, so maybe I'm not going to do that. All right, let's Okay, so the numbers were 6.78 times 10 to the third. So on my calculator, I would put in 6.78 E3 and 5.55 times 10 to the negative fourth. All right, multiply 5.55 times 10 to the negative fourth equals 3.7629. Now that's what our calculator comes out with. As far as significant figures are concerned, no calculation can exceed the number of significant figures that went in. So I had 3 significant figures that went into the value in the first. I multiplied by something that also had 3 significant figures. So my answer here cannot have more than 3 significant figures. I'm going to have to round this. In my rounding, I'm going to round to the third significant digit, which is the 6. I look to the digit to the right of it. If that digit is less than 5, we just cut off those values. If this digit is 5 or greater, we round up. Since it is less than 5, our value here is going to be 3.76. Now we'll get more into our rules for significant figures when we start looking at doing calculations, but that's kind of the general rule that you would want to follow, especially when we're multiplying and dividing. When we're multiplying and dividing, we can't have more significant figures coming out of the answer than what were put into the answer. So whatever number we are multiplying and dividing by, whichever one has the fewest significant figures, that's how many significant figures we're going to put into our answer. So let's look at the second problem there. (2.99) times 10 to the negative ninth divided by 4.03 times 10 to the negative sixth. So doing the same kind of thing, 2.99 e negative ninth divided by 4.03 e minus 6. My calculator gives me a really long number. Calculator spits out this 7.419354839 times 10 to the negative fourth. That's what my calculator spits out. Same kind of thing that we saw in the first problem, though. Significant figure rules do apply. I have 3 significant figures in this answer, or in this measurement, 3 in this one. So I'm only going to have 3 in this one as well. That means the 7, the 4, and the 1 are significant digits. Everything else is not. I need to round the 1. I can see that I've got a 9 next to it. So that's going to round the 1 up to a 2. 7.42 times 10 to the negative fourth is going to be the answer we're looking for in that spot. For the last one here, for at least this one, okay, Trenton, come back to number 2 in just a second. So in number 3 here, we have 7 times 10 to the 3rd to the 4th. So 7e to the 3rd. So there's my scientific notation, 7 times 10 to the 3rd. Now I got to go to the 4th power here. On my calculator, that's the exponential button, xy. If I click on this and then put in my value 4, it'll give me the value that I seek, raised to that power. On the TI, similar kind of functionality. It's y to the x instead of x to the y. Don't ask me why that's the case, but I put it in 7 times 10 to the 3rd raised to the power of 4 equals, and in both cases, 2.401 times 10 to the 15th. I only had one significant figure in the measurement, so I can only keep one here as well. 2 times 10 to the 15th is going to be the correct answer for that problem. Now, coming back to the, we had a question about number 2. Let me pull that one up again and show how I inputted it into the calculator. We had, correct me if I'm wrong in the chat here. I can't share 2 screens at the same time, unfortunately. That's the problem we were doing, right? 2.99 times 10 to the, is that negative 5th or negative 11th? Divided by 4.03 times 10 to the negative 6th. Okay, oh, it's 9. Okay. So 2.99 times 10 to the negative 9th divided by 4.03 times 10 to the negative 6th. So the input there, I can show it on either of these, it's fine. 2.99 exponent negative 9 divided by 4.03 exponent negative 6. TI calculator does not put it into scientific notation for me. I'd have to do it myself. The scientific notation there would be 7.42 times 10 to the negative 1, 2, 3, 4. So 7.42 times 10 to the negative 4th. If you're looking at a Casio calculator or one similar to this, 2.99 times 10 to the negative 9th divided by 4.03 times 10 to the negative 6th. (7.42 times 10 to the negative 4th that time. So again, the real trick here, the real key is you have to be able to put in the values into scientific notation and do so correctly. And so this is where we're going to stop for the day. We're right at class time. And so what I want to point out to you, we've already talked a little bit about these significant figures and calculations rules. We started to apply that when we were doing those calculations of scientific notation. You're going to see more of that. And so that's where we'll pick things up on Wednesday. What I would encourage you to do is I'm going to reopen the math review because now you should have all the tools that you need to do it. So if right now you're showing a 0 or a low score for that, I encourage you to go back, get into Connect, and go ahead and do more of that. Try to bump your score up now that you have some more information ahead of you. And then on Wednesday, we're going to pick up and talk about significant figures. And we're going to get into also some discussions more about matter. And that'll take us into the next part of the unit. So if you have any questions, feel free to drop me a message in Remind or send me an email. But that's all for today. Have a good afternoon.